Okay, so let us start. So now next one is we will discuss about the pitchfork bifurcation. So I hope you remember pitchfork bifurcation. Can anyone tell me what is a pitchfork bifurcation? What is the pitchfork bifurcation? I had discussed pitchfork bifurcation for one-dimensional maps. So please tell me what is a pitchfork bifurcation? No, it is not exchange of stability. Exchange of stability is known as the transcritical bifurcation. When you vary the parameters, okay, like suppose there are two fixed points before parameter change, A fixed point and B fixed point. A fixed point was stable, B fixed point was unstable. Then you vary the parameters, then you came to know that A fixed point is now unstable, B fixed point is not stable. That means they have interchanged their role. That is known as a transcritical bifurcation. They have interchanged their stability. So that kind of qualitative difference structure is known as a transcritical. But what is a pitchfork bifurcation? Pitchfork bifurcation, you can just use your just common sense. What is a pitchfork? I gave you an example of Aquaman last class. Okay, how he holds the trident, isn't it? He holds the trident. It looks like this, isn't it? He holds this trident. So pitchfork is exactly the same. This is the pitchfork. So pitchfork will look like this. So from one fixed point, you are going to something like three fixed points. Yes, so that is a pitchfork bifurcation. Okay. So the same bifurcation, we will look for these continuous systems. Okay. So this is a good thing that you see similar kind of bifurcation in all the systems. In 1D maps also we saw pitchfork bifurcation. In 1D continuous systems also we are going to see pitchfork bifurcation. In 2D maps, pitchfork bifurcation again. So these are well known to any system. Okay, any system you take. Just the condition will be different depending on the type of continuous or discrete system. But yeah, let's start. So pitchfork bifurcation. So this is usually seen in systems. This is usually seen in systems with symmetry, right? This is usually seen in systems with symmetry. What do I mean by that? So whatever our consider our 1D continuous system x dot equals to f of x. Here I mean that f should be symmetrical. Even if it is not symmetrical, still this bifurcation can occur, but you can get an idea that if your map f, like if your function f is symmetrical, when you draw this function, then there is a high chance that this system, 1D system, will show the presence of pitchfork bifurcation. Okay. For that, we will take one example, and I told you last class, like while taking the example for saddle node bifurcation, I took a parabolic kind of figure. We had something like r plus x square, x dot equal to r plus x square. Why we took that example? That is the simplest example saddle node bifurcation. So similarly, we will start with the simplest example showing the pitchfork bifurcation. So what is the simplest example? In the literature, if you see, a simplest example is x dot equals to rx minus x cube. Okay. So x dot equals to rx minus x cube. What happens? What happens if you change x to minus x? You can see the structure is not changing at all. Why? If you see, you have to replace x with minus x on both LHS and RHS. Yes. So what is this? If you do that on the LHS, what is this? dx by dt equals to rx minus x cube. So if you replace x with minus x now, so what it will happen? d by dt of minus x equals to r times minus x minus of minus x cube. So this is same as x dot equals to rx minus x cube, isn't it? Yes. So you can see that the equation stays the same. The equation just stays the same, even if you interchange x with minus x. So that's what I mean by symmetry. That's what I meant by the symmetry. Okay. So let us see how this function looks. How this, if you plot rx minus x cube, I strongly suggest, while I draw, you can draw in Desmos this one and see how this curve changes, the shape changes. So what you can do, suppose for r less than 0, let us do for different values of r. For r less than 0, how this function will look on this plane of x dot versus x. What happened? If you take minus common here and take a minus common here, it is rx, and still it will be x cube, cancelled out. Yes, it is minus of minus. Therefore, we are able to do this. Okay. So you can see that it is symmetry. This is saying that even if you replace x with minus x, it still stays the same. So this is symmetrical. Right? Fine. Now, I am asking for r less than 0. We will take different values of r. R less than 0, r equal to 0, r greater than 0. That's the only possible cases for r being a real parameter. Yes, it can be positive, it can be negative or 0. That's it. So for r less than 0, how this curve looks like? Can you think? For r less than 0, you can take different examples and convince yourself that it will look something like this. Right? Rx minus x cube. To make you visualize what you can do is just see on Desmos. But I would strongly suggest that think how to draw this curve. If Rx minus x cube is being asked to you, you have to draw this curve, right? Yes. So how you can draw this curve? Think about that. I will tell you one very nice thing. When x is very, very small, if x is very, very small, you take the higher powers, 0.01 suppose. Take the square of it. What it becomes? 10 to the power minus 4, 0.0001. Take the cube, it even gets smaller. So when you take a very small quantity and take higher powers of it, then it gets to very small quantity, isn't it? So therefore, for less value of x, that is closer to 0, you can see around these points, see my cursor over here, around these points, you can see that x cube will be very, very small because x is very, very small. Okay, if x cube is very, very small, you can just ignore this x cube for this area, for this region. Okay, if you can ignore that x cube, what it turns to? It just turns to a straight line, Rx. Can you see? See, for x less than 0, for x, yes, you can say that. But we have to show it using proof. But I'm therefore, since I don't know exact bound, I'm just telling that very small values of x. For x very close to 0, you can ignore x cube, right? If you ignore x cube, because it's a very tiny quantity, if you ignore x cube, what does it? It becomes just this Rx. Yes, because minus x cube you just can neglect, right? It becomes Rx. And since you have taken R to be less than 0, what does it mean? It has a negative slope. That means it will make an obtuse angle. Yes. So can you see nearby x-axis, that nearby a straight line? Can you see an approximation to a straight line over here? I am asking you to see around this region. Okay, this region you can admire that this is a straight line. Yes, close to x-axis. But what more can you admire is it is making a obtuse angle, right? That is a negative slope. So you can admire that if r is less than 0, that it is making a negative slope. Yes. Yes. So I am giving you an idea of how to make a plot. How to make a plot. Yes. And moreover, you know, this guy should pass through origin also, Rx. Why equal to Rx? But R is less than 0. That's what I'm saying. So that will pass through origin, and since R is less than 0, the slope, it will make an obtuse angle with it. So therefore, you can see why it is not like this, rather it is like this. Yes. And once you get one of the straight lines, then you know it is x cube, and you can just draw these lines, that curve. That's how you draw this Rx minus x cube. Can you see, just by starting from a very basic observation, you can draw the whole structure. Yes. That's how we are doing this. Okay. Anyway, so you draw the structure, then I ask you, what happens here? What happens here? See, you can see that any tangent you take, over here it is less than 0, the slope is less than 0, right? That means it is stable. That means the exponential part will decay. Last time, the perturbation effect. Yes. So what will happen if it is going to decay? The trajectory will come closer here, right? Similarly here, still here in this side also, the slope is negative. Therefore, that exponential part will decay. If the exponential part will decay, it will approach the fixed point instead of going away. That means, approach means it will come this way. Can you see now that this is a stable equilibrium point? Because the nearby trajectories are approaching towards it. So this guy I can mark with blue. All right. So this is the stable equilibrium point which exists for r less than 0. Now, what happens when r equal to 0? What happens when r is equal to 0? That's interesting. For r equal to 0, you see x dot is just becoming like minus x cube, which we discussed last class, isn't it? So how the structure will look like? This is x, this is x dot. Can you tell me how the structure will look like? It will be, still follow the, but due to this cubic term, it will be, you can think of it will be pasted, it will be compressed along vertical direction. Think that I'm compressing this curve on the top I have drawn on this side, on the vertical axis. Okay, that means I'm pressing it. If I'm pressing it, do you admire that you will see something like this? Something like this, like not a good structure, but yeah, something like pasted structure. You can see that now it is taking a bit more asymptotic behavior towards 0. But anyway, you can admire this using graph and all. But let us again see that it doesn't change the slope anyway. It doesn't change the slope. Again, here you have a negative slope, so trajectories are coming here. Again, here it is a negative slope. Again, trajectories are coming here. Okay. So again, it's a stable equilibrium point. It persists. Okay. Now, what happens when r is greater than 0? That's the case which is more interesting. For r greater than 0, what happens? What do you think? How this function will look? Of course, it will be a straight line. Of course, it will be a straight line. Like as per our nearby 0 rule, nearby 0 observation, it will look like x, and this is x dot. And since here this straight line was a negative slope, and now since you have a positive slope, so it should be somewhat looking like nearby, somewhat looking like this, because it has a positive slope, isn't it? It has a positive slope, so it will make an acute angle with the x-axis. So the nearby 0, it will look something like this. Of course, fine. But after that, no longer your theory is valid, because now you cannot say x is very close to 0. X is increasing if you go further. Okay. Then your structure changes. Into something like this. I will draw. You can think that, you can admire that it is the case. Okay. But still this is valid. Nearby 0, you can still see that it is having a positive slope. Fine. Now you can see that how many equilibrium points are there? Yes. How many equilibrium points are there? But how are you calculating? See, fixed point. How many? You should say equilibrium points. Should warn me. So how many equilibrium points should be there? You can see equilibrium points are the points where x dot is equal to 0. Where x dot is 0? On these points 1, 2, and 3. So previously only 1 point it was there. Now suddenly you see 3 points. Now you can understand why we drew this trident. Previously 1, then 3. 1, 2, and 3. Okay, fine. So now you see these three equilibrium points, but what remains is to analyze their stability. Can we analyze the leftmost fixed point? Sorry, the leftmost equilibrium point. So you can see the leftmost equilibrium point over here, it is still making an obtuse angle with the x-axis. So the slope is still negative. Therefore, trajectories are coming towards it, towards that. After the intersection also, the slope is negative, making an obtuse angle. So therefore, still it will be decaying because the slope is negative. So it will come towards the equilibrium point, isn't it? So therefore, still again on that side also it is coming towards. You got this ideology of observation? Okay. So on this side, this is the equilibrium point, isn't it? Now see on either side of the equilibrium point. There are two sides of the equilibrium point. See on the right side of the equilibrium point. On the right side of the equilibrium point, it makes a negative slope still. It is more than 90 degrees. So therefore slope will be negative, tan theta, negative. Yes. If it is negative, you already know trajectories will decay, the exponential negative. It will decay. If it is decaying, that means comes closer to the fixed, to the equilibrium point. Therefore, this arrow is given. See on the other side of the fixed equilibrium point, that is this. Yes. You can see it is still making obtuse angle still. That means it is still decaying. Okay, it is still decaying. So what happens to these trajectories? They also decay and approach the fixed equilibrium point on the other side. So from this you can conclude that both sides trajectories are coming closer towards the equilibrium point. Therefore, it is an stable equilibrium point because nearby trajectories are approaching towards it. So you can see this is a stable equilibrium point. Done. Okay. What happens to the other two? Can you think? What happens to the other two? Let's think about the origin. Now you can carefully see that you already got free, one for free, the direction near the origin on the left side. So this is a fixed point. This is an equilibrium point. And on the left side of the equilibrium point, the trajectories are moving away, isn't it? On the right side of the equilibrium point, what happens? It is still away. Why? Because it is making a positive slope. You can see it is less than 90 degrees, so it will move away. So can you see that this origin trajectory should be unstable because nearby trajectories are moving away. So that I denote by red. Okay. Now what happens to the last equilibrium point? You got one side of the equilibrium point for free, one direction. This trajectory is coming towards this equilibrium point. Now on the other side, what happens? The slope is still negative, making an obtuse angle. So therefore, tan theta will be negative, slope will be negative, so it will decay and approach towards. So therefore, you can see this direction here. Yes. So therefore, this guy should be stable. Yes. So can you see what kind of structures we are going through when R keeps on changing? When R is less than 0, when the parameter R was less than 0, you had this stable equilibrium point at the origin. Then when R is equal to 0, the stable equilibrium point still persists. Okay, then when you increased R value more than 0, that you made it positive, then what happens? Then suddenly birth of 3 equilibrium points took place. Actually, additionally, the equilibrium point at the origin is still there, but it was stable previously. Now it became unstable, which I am colored red. Then additional dynamics appear. That means additionally 2 more equilibrium points appeared, okay, in your structure. So that means there is a qualitative change, and such a qualitative change is known as bifurcation. And this is of course different from the saddle node bifurcation, isn't it? Do you think here anything collision happens? No. So they are just getting birth, like due to the structure of the function. So suddenly from one equilibrium point, you see three equilibrium points. Okay. So that's what is the trident shows. Here you had one equilibrium point. Suddenly here you have three equilibrium points. Okay. So now what we will draw is the bifurcation diagram. I told you what is a bifurcation diagram. What is a bifurcation diagram? Maybe we can go it in the next page. Now you understood this concept. Okay. So let's go to this bifurcation diagram to draw this bifurcation diagram for a pitchfork bifurcation. Bifurcation diagram means to actually analyze how this number of equilibrium points changes as we vary the parameter r. I think you yourself you are convinced that with r less than 0 there was one equilibrium point, then for r greater than 0 three equilibrium points. So we want to understand what happens when you change the value of r from negative to positive. Okay, to understand this phenomenon. Okay. All right. So what we do to understand that, you take one of the coordinate of the equilibrium point, okay, on one axis. Then you take the parameter r on the other axis. That's it. That's all you have to do. Okay. So that's what we are doing it here. Okay. So what we do, you take the parameter r, parameter on the x-axis, r parameter on the x-axis, then one of the variable, state variable on the y-axis, that is x. And you have only one variable, one state variable here, okay, that is x. But in higher dimensional system also you can do this bifurcation diagram. But in higher dimensional system you will have more than one variable, isn't it? X, y, z. But still you can take one of the variables, any one. Okay. So what this shows for r less than 0, can you see this is 0. For r less than 0, what we have? For r less than 0, what is the equilibrium point we have? Number of equilibrium point is 1. But what is the x coordinate of the equilibrium point? It was staying at the origin. It was staying at the origin, isn't it? X is 0 there. So therefore, where should I plot for r less than 0? Where should the plot be? It's on the x-axis. It's on the x-axis, isn't it? Because x equal to 0. Now it will be for r less than 0. X star equal to 0 is stable equilibrium point. So I will draw that in blue. Do you think for r less than 0 means for any r less than 0? Any r less than 0, yes. So see, for this r, you have this equilibrium point here. For this r, you have here. Fine. But I want to draw for a tiny change in r. That means you will see a lot of dots over here, which will appear to you like a straight line. Fine. And I'm drawing this in blue. Actually, yes, I could cover all this of this. Yes. Yeah. So whatever r less than 0 you take, it is stable. Fine. Now what happens at r equal to 0? We saw it is still stable. At r equal to 0, it is still stable. But the moment you increase r to positive, r greater than 0, the moment it becomes 0.0001 also, still you will have three equilibrium points. Okay. And how three equilibrium points? Can you tell me what are those three equilibrium points? One of them is still 0, isn't it? One of them is still 0, we saw at the origin, which became unstable right now. Okay. So did it become unstable right now? So for r greater than 0, what do you think? What do you think happens? The equilibrium point is still there, but now it is not stable. Rather, it is unstable. So if it is unstable for r greater than 0, I will denote it by red lines, but dotted. Okay. So let's go here. You can see that, yeah, I just drew it here like this. It is still on the x equal to 0, isn't it? Do you agree? Why? Because the equilibrium point is still at the origin. for r greater than 0. Yes. So therefore, it is on the positive r axis. You can see for x equal to 0, it is a unstable equilibrium point. Okay. Now is the important part which you need to understand is what is we found this equilibrium point, fine, but what are this what are the coordinates of this? Can you tell me what are the coordinates for this? Yes, you found it out, right? How you will find out? Just yeah, just to show that x dot equal to 0. Yes, just to show x dot equal to 0. When you do x dot equal to 0, rx minus x cube equal to 0, right? So x times r minus x square equal to 0. So you can see that x star equal to 0 is an equilibrium point. Root over r minus root r is an equilibrium point. Are you getting? Are you getting? Just x dot equal to 0 and just solve this equation, nothing else. Okay. So you can see that 0 is here. Now minus root r is here. Minus root r is here. This is plus root r. What do you conclude? The distance is same, isn't it? On the positive side, it is root r. The distance is root r. On the negative side, still the distance is root r. It's on the negative axis, but the distance is the same. Distance is the same. Okay. But you got an idea. You got an idea here how the fixed point is varying with the parameter. How it is varying with parameter? It is varying with parameter as a root function of the parameter. R is a parameter, right? Can you see that it is a x, the fixed point here, the equilibrium point here is varying as a root function of the parameter r. Because why I am saying this, because x star, the equilibrium point is equal to root r parameter. This is the most crucial thing. No, this is the most crucial thing. So how you think now? I told you here x star equals to plus root r and x star equals to minus root r. So for this is for r greater than 0 yet, right? Right. So now here additionally there will be two more equilibrium points. Yes, one on the positive x and one on the negative x. Yes, and how they will vary? They will vary as a root function of r, right? So therefore, will it look like this? Do you think? Will it look like this? Yeah, but I am asking because if x equal to plus root r or minus root r, and this is for r greater than 0, that means you know r is greater than 0 now. You are on the right hand side of the axis. So now the fixed point, we are plotting the fixed point here, x star. Yes, sorry, the equilibrium point. So I'm asking whether it is right to show the straight line on both sides. You can see that one is positive here, one fixed point is positive, which matches. One fixed point is on the negative axis, which matches this one also. Is this correct? How many of you think this is correct? How many of you think this is correct? Hmm? X is minus root r. X, which you are drawing on the y-axis. Which you are drawing on the y-axis. So therefore, it will not be on the other side. It will be on the top bottom. It will be on the top bottom. Yes. But is this correct? How many of you think it is correct? Do you think this is correct? Everything is satisfied. One is lying on the positive axis. Of course, one is lying on the positive axis and the same distance. The distance between this and this is also same as the distance between this and this, which is same governed by root r and minus root r. Now, is this correct? What do you think? How many of you think this is incorrect? How many of you think it is incorrect? Four people think 5 people think that is incorrect. 6 people think it is incorrect. Okay. What about others? They think that it is correct. Is this, how many of you think it is correct? Yeah. If no, then yes. So many people think this is correct. Why? Make a decision. I'm asking you to think. I could just plot it and go to the next version. But I ask you to think because this is the place where you think. After that, no. Is this correct? Why? Why? If it is incorrect, why it is incorrect? Suppose I will tell you one thing why it is incorrect. Yeah, suppose if I write, if it was, suppose if it was x star equals to r and x star equals to minus r, then yes, it varies with a straight line, right? If x star equals to r instead of root r, I'm saying if x star equals to r and x star equals to minus r, then this varies with a straight line, right? This is just like y equals to x line. But when I ask it is x equals to root r, it is like y equals to root x. So therefore, and y equal to root x, you already know that it is not a straight line. It is a non-linearity, right? So definitely it will not look like a straight line. Okay. So it should look something else. It should look like a parabola. Yes, Mr. Anandik is correct. So it should look like a parabola. Okay. So something like this you can expect in your exam. Okay. So something like this can be given to you and it will be asked, does this represent pitchfork bifurcation? If no, kind of draw the correct pitchfork bifurcation. Okay. Conceptual question. Fine. Something like this I am telling you. So this is incorrect. This is incorrect. So, oh no. Fine. Actually, the size is too big. Ah, I see. How it should look now? That's my question. How? Hmm? How it should look? That's the question. So it should look like a parabola. It should look like a parabola, right? So let us draw that. Something like this. Okay. Yes. It should look like a parabola. Because why? Because it is varying like a root r, y equal to root x. Right. Then now my question to you is another visualization. All are visualization. Now there is a positive, this is a positive equilibrium, right? This is something like a positive equilibrium lying on the positive x-axis. This is a negative equilibrium lying on the negative x-axis, right? Now what I'm asking you is which one is stable and which one is unstable based on this diagram. You know here that on the fixed point, the equilibrium point lying on the negative side is positive, is stable because I have drawn it in blue. And again the equilibrium point on the right hand side of the x-axis that is greater than 0 is also blue. So both of them are stable. Both of them are stable because nearby trajectories are coming towards it. So therefore both negative and positive equilibrium point, I should mark it blue because it is stable. Got it? So stable, I'm coloring it blue. So both of these arms, both of these parabolic arms, what should I color? Red or blue? Both of them. Both of them. Why? Because both of them are stable. Okay, you can analyze now. Yes. Can you see this bifurcation structure now? This looks like the trident. This looks like the trident I just told you here. Okay. So therefore, this is a pitchfork. It has one line and 3 more lines there. So it looks like a pitchfork. It's like a pitchfork. So therefore, this is named as pitchfork bifurcation. Fine. Okay. And pitchfork bifurcation, what happens? A stable equilibrium point turns into 3 equilibrium points with one stable and symmetrically placed stable points. Okay, stable equilibrium. All right. So I will tell you the pattern over here, how it went. Here you see only one equilibrium point. Here you still saw one equilibrium point, but here you saw 3 equilibrium points. Okay. So you can see when you vary the parameter from negative to positive, the transition of fixed points, the equilibrium points is 1, then again 1, then again 3. This is the transition of number of fixed points, equilibrium points. Okay. Here, it will increase as root r. The fixed point will increase as root r. Bifurcation can occur for any other polynomial function. What is meant by number of bifurcations? Oh, see, for this system, this is the simplest system which shows this striking structure. This is the simplest structure, Rx minus x cube, which shows this striking structure. Now, what I suggest is you can do it. Now, I can guarantee you, if you do Rx minus x to the power 5 odd function, then qualitatively the picture will be the same, isn't it? So for that, you can see again pitchfork bifurcation. Yes. We don't know. You have to find out how many. Okay. But as I told you, pitchfork bifurcation occurs in systems with symmetry. So, okay. So you can try for different maps. Maybe Rx plus x cube. Rx plus x cube you can try. Okay. So this is the simplest one-dimensional system which can show you the pitchfork bifurcation. Okay. Fine. And the one more important thing is sometimes we were quite lucky. We were quite lucky that we saw after the bifurcation, two of them are stable. Two of them are stable equilibrium points. But there are cases where after bifurcation, the two equilibrium point which I drew blue are unstable. That means I have to draw red. Okay. That is also possible, but I did not discuss it here. Okay. That is also possible. Since the bifurcating solution after the bifurcation at r equal to 0 are stable, this is something known as something better. It is known as something known as a supercritical pitchfork bifurcation. Okay. Because after the bifurcation, the solutions are stable. Why? Because bifurcating solutions are stable. Fine. Okay. Okay with you? Yes. Now there might be a case which is like this. X star. This is R parameter. Where here for R less than 0, you have this stable equilibrium point. Then it becomes unstable. Like this is unstable anyway. But these guys also become unstable. This also gets unstable. The bifurcating solutions are unstable. If the bifurcating solutions are unstable, then it is subcritical. It is known as a subcritical pitchfork bifurcation. Okay. But it is still a pitchfork bifurcation because you still see the pitchfork here, isn't it? You still see the pitchfork here, but depends. when I call supercritical or subcritical, it depends on the stability of after the bifurcation. If the two symmetrically placed equilibrium points are stable after the bifurcation, it is known as a supercritical pitchfork bifurcation. If it is unstable after the bifurcation, it is known as subcritical pitchfork bifurcation. The same applies for any kind of bifurcation. Sir, which one? That is assignment. That is assignment. I suggest you find a system which shows this behavior. Okay, because I told you one system which shows after the bifurcation it shows blue line, right? Now I ask you as an assignment, which you will show me class coordinator is absent. If class coordinator is absent, then the subclass coordinator will become Miss Irene Davis. Okay, so Miss Irene Davis should note it down that this is an assignment. Okay, so the assignment of when I return back would be this one. To show pitchfork, to show the equations, to construct and the equation for a subcritical pitchfork bifurcation. Okay, and convince yourself that you will see something like this. Or if I have done something wrong, you may correct it when I arrive. Okay. Okay, let's look into the next bifurcation, that is the transcritical bifurcation. Okay, so I told you let's do till 1. After 1 we go and again come at 2, right? Or when we should start?